Hello friends, very good evening from India and very good morning in USA, West Coast, that is Pacific time. I am Avinash Shirode, President, Nashik India chapter of National Space Society. Our very eminent speaker for today is Mr. Al Globus. He is a former software engineer at NASA Ames and he is also a director of National Space Society. The subject of his presentation is Space Settlement, ELEO, that is Equatorial Low Earth Orbit. Now let me introduce Al Globus.
So this book, the ideas behind this book revolutionized my life. I'm Al Globus, sorry. I just got introduced, so I don't really need to tell you that. This is a book written by Gerard O'Neill, a Princeton physics professor, on how to build space settlements. And he had this beautiful vision of these different settlements. You can see the interior of one of them here. But here we are. This was done in the 70s and the 80s. Okay? And here we are in 2020, and none of this has gotten done. And when I was thinking about, well, why hasn't it happened? I realized that it was simply too difficult. It's too far away. It's too massive. It's too big. There's too many things you have to develop all at once. And the result is no progress at all. So I went to look for some way to simplify the task, to make it much, much, much easier. Not a little bit easier, but much easier. And the results of that, oh, crud. There we go. Oops. Okay. The results of that investigation are what I'm going to tell you about in this talk. And they're also described in one chapter of this book, The High Frontier and Easier Way. And that's exactly what it is. It's Gerard O'Neill's ideas about the high frontier. But instead of doing it the way that O'Neill suggested, having another approach, which made things much easier. Now, I'm going to go over that approach right now, and many of you may not understand it this time. However, I'm hoping by the time we get to the end of the talk, you will understand it and we'll go over it again. Okay, so the first key is to make your settlement close to Earth. The settlements O'Neill are located at lunar distances from Earth. It's just too far. It makes it much more difficult to do things. I'll present evidence about that. And when you make it close, you want to go into low Earth orbit. That's what Elliot, let me get my pointer here. You can see this red pointer. The LEO stands for low Earth orbit. And that just means close to Earth. The E means equatorial, which means as close to the equator as possible. So ELEO is an orbit that is close to Earth and close to the equator. And if you put your settlement there, they won't experience much radiation. And that reduces the amount of mass of the system enormously. The second key is to make the settlement small. And I won't go through the explanation of this now, but we will see it. Basically, if you rotate at 4 RPM instead of 1 RPM, RPM means rotations per minute, you can make a settlement much, much smaller. And still, people will be okay. They will get a little ill, but they'll be all right. Now, if you put these two things together, you get a settlement that is so small and so light that you can kind of take the vehicles in development today, not the ones that are flying routinely, but the ones that are in development, and they may have the proper characteristics to launch the space settlement from Earth, which was thought could not possibly be done. Right? And then the last key is don't go straight for building the settlement. Start with where we are, the International Space Station. Make small space hotels, make them bigger and bigger until they're as big as a settlement, and then build a settlement. Okay, so we're going to spend the next hour exploring these 4 keys. Okay, but before we do that, we need to agree on what a space settlement is. Now, if you don't like this definition, that's fine. But for the purpose of this talk, this is what I'm talking about. So if you're looking at something and wondering what it is, and it's in space, and people come there and they work for 6 months and go home, that's not a settlement. That's a space station. Okay? Now, if you want another facility and people keep going on recovery a couple of weeks and they seem to be having a really great time and they don't do much, you're looking at a space hotel. If you hear the people talking as if they were going to live there for decades, and if they're raising their children, okay, then you know that you're talking about a space settlement. And that whole bit about raising children, that's extremely important. It drives the design of space settlements. Okay, here's a settlement that was invented in the 1930s, before Gerard O'Neill's work, which was in the 70s or 80s. And it's called the Bernal Sphere. Bernal is the man who created it. And this living area right here is a spherical space. That's why it's called the Bernal Sphere. Now these things here, you can see the red dot moving, are for agriculture. That's where you grow the food. These are mirrors to bring natural sunlight inside the habitat. Okay. Here we have solar arrays for power. Not enough power, but it's the artist's concept, not an engineering diagram. And here's communication gear. Now, if we go inside, this is what it looks like. Now, there's a couple things to notice. First of all, we're on the inside of a sphere, inside of a ball, right? This is what it looks like. And then also notice that these people here, they're not floating around. When you see videos of astronauts in the International Space Station, they float around. Now, they're not really floating, but it looks like they're floating. Okay. So what's going on? Why aren't these people floating? They're in space. Well, they're in space, but this whole system rotates. This whole settlement rotates. And it rotates fast enough that it feels as if they're on Earth normal gravity. And to understand a little bit about that, suppose you're in a car and the car takes a corner fast, you're going to be pushed off to one side, okay, by the force of the turn. Now, if the car was to go all the way around in a circle, okay, and then so you would be pressed up against the door the whole way around. That's what's happening to these people. Instead of pressing up against their shoulder, it's pressing up against their feet because there's no gravity to pull them down. There's no real gravity, there's pseudo-gravity. Okay. So here is another settlement. It's called the Stanford Torus. It is a classic, and it is one of the basis of comparison that we're going to be looking at today. So we're going to be looking at being able to improve on the Stanford Torus and modifications of it. Now, the Stanford Torus rotates at 1 rotation per minute because it's thought people would get sick if they rotated faster, which turns out to be true, but maybe not as important as we thought. That means that this has to be 1,790 meters across, almost 2 kilometers. That's a big system. And you see this brown material here. It really should be gray. It's lunar regolith. Regolith is just crushed rock, and it's what the moon is covered in from a meteorite bombardment. And this, the Stanford Torus is supposed to go at a point called L5, which is the lunar distance from Earth. And if you put a settlement at L5, it'll stay there. It'll also stay there. You put it at L4. And L4 and L5 are equidistant, equal distance from the Earth and from the moon. Right? So they're a long ways out. There's a lot of radiation out there. And this lunar regolith that has been delivered by a sort of electromagnetic catapult to the site, it's radiation protection. That's what it's for. It weighs millions of tons. So the system is big because they don't want to rotate fast, and it weighs millions of tons because they wanted to put it somewhere where you can get lunar materials relatively easy. Okay, so here's the interior. Again, the people aren't floating around. Okay, that's because this is rotating, as we said, at 1 RPM. Here's another settlement. This is called the O'Neill cylinder. It was interesting to try to see how big they can make a settlement. So here's something that gives you an idea of how big settlements can ultimately be. This is one of the last times we will look at anything this big, because what I'm concerned with now is how do you make the smallest, easiest, closest settlement that you possibly can. Okay? This is a beautiful vision, but it's too hard to do right now. We have to do something easier. Okay. This is Colpin 1. It was an attempt to reduce the mass of the Stanford torus and the O'Neill cylinders to something more reasonable. It rotates at 2 RPM, 2 rotations per minute, and that means it has to be 450 meters across. Now, I should tell you why the name, Kalpana, obviously an Indian name. Kalpana Chawla was a NASA astronaut. She was born in India, but she became an American citizen and was a NASA astronaut. And the shuttle that she was in, the Columbia, disintegrated over Texas on the way down, which was, sad for everybody, but particularly for us in our building because Kalpana Chawla used to do computational fluid dynamics, and she did that in the office next to mine. So it was a bad day, and my homage to her is to name these settlements after her. And so think of her when you think of that name. So in any case, this thing rotates at 2 RPM. It's 450 meters across. That's how it has to be if you're going to go 2 RPM. Okay, and here's the interior. Interior is done by the great contemporary space artist Brian Versteeg. Give you an idea. Okay, so now we understand what a space settlement is, and you'll notice that we haven't talked about Mars and the Moon yet. Okay, and most people think, oh, you're going to colonize space, you're going to sell space, you're going to go to the Earth. I mean, you're going to go to Mars, or you're going to go to the Earth. Are you going to go to the Moon? Mars and the Moon. That's what you get to try to do, even though I keep saying Earth. But we haven't looked at that at all. I promise you we will look at it, and there's a reason why I'm ignoring it so far. So why would we settle space? Survive and thrive, okay? Survive. Civilization, humanity, life itself depends solely on the Earth. Okay? If something goes wrong with the Earth, and if someday something will, no matter how hard we try to stop it, someday things will go badly, then we're stuck. We lose Earth, we lose everything. I mean, literally everything, every relative, every friend, every accomplishment, every book, every TV show, everything, okay? So we want to spread out. We want to be in more places than just on Earth so we can survive. Okay? The second thing we want to do is we don't want to just hang on by our fingernails. We want to thrive. And what do you need to thrive? A garden that's thriving is getting plenty of energy. It's getting lots of sunlight. It's getting plenty of water. It's getting plenty of materials, okay? So what does that mean for us settling space? Well, in this solar system, the energy available to Earth, to space, is 2 billion times more than on Earth. That's all the energy you could possibly want for a long time. And materials, if you just take the asteroids, asteroids are just rocks that are zipping around the solar system every once in a while running into us. If you took those asteroids and you tore them apart and you put them back together as space settlements, you could get hundreds of times the total surface area of the Earth in living space. Hundreds of times. Support a population measured in trillions. And this is, I believe, what's driving what I call the biological imperative. Hundreds of millions of years ago, there was no life on land, only in the waters of the ocean. Okay, obviously that changed because we live on land. We can go swimming, but we live on land. Okay, so there was a movement of life from ocean onto land. And the ocean has still got plenty of life in it, but now you also have the land. Similarly, today we are on Earth and we're pretty much stuck on Earth, but we know more or less how to get into space. And that is what we are doing right now. And that is what you are participating in. And I invite you to participate in it very strongly for your whole life. Okay, so let's finally get to the Mars and the Moon. Okay. Here we have a settlement on Mars. Here we have a base on the Moon. Now you notice that some of this lunar regolith here is piled up around these modules, these habitation modules. That's to protect from radiation, because there's a lot of radiation on the surface of the Moon, and there's a lot of radiation on the surface of Mars. Okay? So you need something to protect you. And this, by the way, is completely inadequate for settlement, the amount of protection you've got here. You need 5, 6, 7 meters of material over 5, 6, 7 meters of material covering all the habitations. This is even worse. It's a beautiful vision, but it doesn't have any radiation protection at all. Okay, so what you would really see in something that was protected from space radiation, which is mainly to prevent cancers and cataracts and a few other things, that you would see a large pile of red regolith, red dirt, and stuff sticking out of it here and there. So one of the problems, the problems of space settlement that this Mars and the Moon solve, but don't, okay? Problems are radiation. It takes care of radiation because although they didn't do this here, it's a fairly simple matter to get a bulldozer and just pile up 5, 6, 7 meters of regolith to protect it. So that's a problem. Distance, these are very far away. And we will get a slide about this. And more than one slide, actually a couple of slides on this, and everything gets more difficult when you move farther away. And that has important consequences. The second is gravity. No matter what you do, on the Moon, you get 1/6 gravity, not 1g, 1/6 gravity. What does that mean? It means your kids are going to grow up with weak bones and muscles. And there's really no way around it. On the Moon, it's a little better. It's 1/3 g. Okay? But still, that's a lot less than Earth normal gamma. What's going to happen to the kids growing up? We have no idea. No idea what's going to happen. And that's completely unacceptable. We're talking about kids right now, okay? Size, you can start small and build up. Obviously, this started small and build up. This did too. Getting mass is no problem. There's tons of materials, and that's why the radiation is not a problem. Okay, so distance. Equatorial low Earth orbit, which is what we're going to be talking about, is 500 to 600 kilometers away. It's very close. The Moon is 382,000 kilometers away. That varies a little bit, okay? But that's basically, it's 760 times further than ELEO, equatorial low Earth orbit. I mean, that's not nuts. And then if you look at the Earth Moon L4 and L5, if you remember, that's where we put the Stanford torus so that it would stay in the same place relative to the Moon and Earth. Those are at lunar distances, okay? So they're the same distance, 382. It takes 3 days to get there. It takes a couple of hours to get to Leo. And Mars is absurd. It's 54 million kilometers away. It's 100,000, that's on a good day, okay? That's when it's close. Other times it's much further away. It's 100,000 times further away than equatorial low Earth orbit, which is, explains some things. It explains this. Space stations are the closest approximation of a space settlement that we have. The first space settlement that America made, the Russians beat us by a couple of years if I remember correctly, was Skylab, which we see here. This is not Photoshop. This is a real thing. As a matter of fact, Photoshop did not exist when this picture was made. Okay? So this has been around since, we've had stations since the 70s. Since 2020, we have had the International Space Station up there, and it's still up there, and people have inhabited it regularly since 2020, for 20 years, okay? That's been up there. This is not Photoshop. This is a real thing. There are no lunar bases. None. There are no Mars bases. There's not even firm plans with funding to build one. Well, how is it? People are actually more interested in the Moon and Mars than they are in low Earth orbit, which is where Skylab and ISS are. What's going on here? Why haven't they built the lunar bases? They're too far away. It makes it too difficult. They're 382,000 miles away, kilometers away. It's too difficult. It's too hard. That's why for space settlement, we want to start in low Earth orbit if we can. And what I think I've contributed to the literature is we can. Okay, so here's the dream of the 70s. It's the Stanford torus. It has a mass of about 13 million tons. This is in kilotons. It has a size almost 2 kilometers. It has a large population. It's about 384,000 kilometers away from Earth. And if we were to launch it with the most capable vehicle under development today, which is the SpaceX Starship, which we will come back to, it would take 130,000 launches to get 13 million tons up into space. It's just, no, we can't do that. Okay, it's too hard. So what that means is you need to use extraterrestrial materials. Okay, so you need a lunar mine or a near Earth object mine. Okay, and you need in-space transportation to move all this material and stuff around. Okay, so let's look at the problems. Radiation, there's a lot of radiation. Okay, it could be solved by lots of mass. You know, these two are linked, but it's too much. It's too far away. Gravity's okay. It can rotate, and kids will get 1G of force on the bone. It's too big to build all at once, and the mass has to be imported from the moon. Okay? So, let's look at the reality of 2020. It was the dream of the 70s. Now let's look at reality 20. So here's the Stanford torus numbers, which you should be familiar with by now. All right. And here we have the International Space Station. That's what actually got built. So you can see it here. Here's the interior. This is obviously not kid-friendly. I hate to think what a bunch of 5-year-olds would make of that lab. Okay. But look at how much smaller and easier this is to do. No lunar mines, no in-space transportation, a mass that's, you know, vastly smaller, size is vastly, everything about it, but it was easy enough to do, okay? And a lot of what's driving all this is the shielding mass, okay? You need, you know, many, many tons of material per square meter, and we will go into this in some detail, in order to protect the residents from radiation, which can cause cancer and cataracts and various other sorts of things, okay? So here is a study. This was done in the 1975 summer study that was conducted at NASA Research Center in Stanford University, where most of these ideas got fleshed out under the leadership of Gerard O'Neill. Okay. So given different shapes for settlements, here's the amount of mass that's needed for the structure, for the, you know, the pressure vessel and so forth. Here's the amount of mass that's needed for air. And here's the amount of mass needed for shielding. And the important thing is not the details, but look at how many zeros there are. These numbers are enormous. And if you look over into this part of the screen, you'll notice that it says between 95 and 99% of the mass of these systems, of these settlements, are radiation shielding. If we can somehow get rid of radiation shielding, that would be a huge win. Okay. So let's go back to our 4 keys, because the first 2 keys do exactly that. The first key is put your settlement in equatorial low Earth orbit, ELEO. That makes it close, 500 to 600 kilometers, and makes it low mass because you don't need any much or any radiation shielding because you're in equatorial low Earth orbit. Then spin it fast, spin it 4 RPM instead of 1 or 2 RPM. That allows the settlement to be small. If you rotate at 4 RPM, your diameter should be 112 meters if you want to get 1G. Okay? And if you put that together, you can take the launchers of today, the SpaceX Starship, which is under development, is doing flight tests, and you can make them, these vehicles are maybe sufficient to take this small settlement and launch it from Earth, which makes everything easier. And then the last step is tourism, okay, which you can get because you're flying these low-cost vehicles. And what that buys you is incremental development. You start with a really small hotel, maybe the size of the International Space Station, and you work your way up until it's the size of Kalpana 2, okay? Because Kalpana 2 is what we get when we apply all this stuff, okay? So it's the size of Kalpana 2 and build it. Now, I'm sorry I didn't go over this, but this is the same picture as Kalpana 1, but you can't really tell how big it is, so I'm going to call it also Kalpana 2. Kalpana 2 is just like Kalpana 1, except that it spins faster, and it doesn't have all the radiation shielding. And you can tell that it spins faster because look at the curvature. You're living in a very curved environment. It's very, very noticeable, which is not something you want to do forever necessarily. but it's a place to get started. Okay, so now let's compare the different numbers for Stanford Torus and for the International Space Station. Kalpana 2 fits in the middle of these two. Okay, it's a significant step from the ISS, but it's not an enormous step that the Stanford Torus is. Okay, and importantly, you could launch all the materials you need for Kalpana 2 with 85 SpaceX Starship launches, if Starship does more or less what we expect it to do. Okay, so that's the smaller step that we're going to take. And here we go over our thing here. So 112 meters, it's 56 meters in length. The images you see are actually twice that width. 500 residents, between 500 and 650 kilometers incremental development. So the radiation problem is solved by going to low Earth orbit. The distance problem is solved by using equatorial low Earth orbits close to Earth. The gravity is solved by fast rotation. The size problem is solved because you make it quite small, and then you can make bigger ones by simply growing the radius. Growing the radius in your mind, we're not actually doing it in physics. I forgot to say this. We're going to do a lot of work today. You're going to have to do a lot of work in this talk. You're going to have to imagine things, okay? Because we haven't built them. I can show you images, but you're going to have to imagine. You have to imagine doing stuff. And one of the things I'm telling you to think about is you're going to shrink this guy down so that it's only 56 meters from here to here, and that's the real size. And the mass, you don't need very much mass because we have a radiation shield. We don't need radiation shielding. All the problems are touched. Okay, here's the interior. Another shot of the interior. Okay, so now let's see why equatorial low Earth orbit has very low radiation and exactly how much it has and whether that's acceptable or not. In the space settlement business, everybody knows you need millions of tons of radiation shielding to protect you from radio space, and you can't launch that from Earth. We saw that with Stanford Torus. Okay. If you're on the lunar or the Martian surface, you got to bury yourself under 5 or 6 meters of local materials. In deep space, depending on what material you're using for shielding, you need between 7 and 11 tons of material per square meter. That's an enormous amount of material. However, there's two ways to deal with radiation. One is by having sufficient mass, which we've been looking at. The other is to use an electromagnetic field to deflect charged particles. And people have designed settlements with these, superconducting magnets and all this kind of stuff in order to do that. But there's a much easier way, and we're into easy for this talk. Okay? The Earth has a magnetic field. And that magnetic field can protect you if you're in equatorial low Earth orbit. The Earth itself can protect you as well. And in fact, below about 500 kilometers or so, you may not need any radiation shielding. And you certainly don't need very much. Okay, that is a very broad claim. You should not believe it at this moment. But when I'm done with the next few slides, you should believe it. So here's what's going on. This is the Earth. This is a cartoon of Earth's magnetic field. Okay. The particles that were considered, and then we're going to be very close to Earth, very close to the equator. You know, the Earth turns and this goes around and around. So the charged particles were considered. It's a problem. The space radiation we're concerned with here is mostly a problem in terms of causing cancer and cataracts and other problems over long term. It's not an immediate thing that'll kill you instantly. That can happen too, but we're not going to talk about it in the interest of time. So in any case, these particles come in high, low, and medium energies. Okay, how fast they're moving. So particles coming from the right of your screen will be absorbed by the Earth. So half the radiation is gone right there. The light and medium particles coming in from the left will be deflected by the Earth's magnetic field and create the aurora borealis. Pretty pictures for the Eskimos. that the heavy particles, such as iron nuclei, moving at relativistic speeds near the speed of light, they're going to go right through this magnetic field and they're going to hit you right in here. And they are very damaging particles, extremely damaging particles. The question is, how many of them are there? Let's go measure. Here we have measured radiation at the International Space Station. Every dot represents a measurement at about 400 kilometers. That's how high the International Space Station is, the ISS is. Blue means low radiation, red means high radiation, and there's about a factor of 500. So red is 500 times more radiation than blue. You'll notice that most of the Earth is covered in blue. Most of the Earth doesn't have that much radiation. Almost all the radiation in this orbit at this altitude is in this South Atlantic anomaly here. Right? It sits over the South Atlantic and almost all the radiation that the astronauts get, they get right here. And if you're on the equator, you don't pass through the South Atlantic anomaly, you don't get that radiation, and radiations are very much lower. But are they low enough to settle space? If you're going to answer that question, the first thing you have to know is how much radiation is acceptable. Okay, we think that 20 millisieverts per year is acceptable. A millisievert is a measure of the damage to tissue, okay? MSV stands for millisievert, 1,000th of a sievert, and that tells you how much damage is done. Now, in the United States, the background radiation is about 3 millisieverts per year, which is not encouraging because that's a lot less than 20 millisieverts a year. But there are large parts of Europe, particularly in Finland and Spain, that receive 10 millisieverts a year in background radiation, which of course is much closer. There are parts of Iran, India, and China and elsewhere where the levels are much higher. The highest levels that are measured is 131 millisieverts per year in Iran. So I spent literally 2 years reading radiation text to come up with the conclusion that the International Commission on Radiological Protection knew what they were doing. They had an occupational threshold. This is for X-ray technicians and nuclear power plant operators of 20 millisieverts per year. And that's where we derive the 20. Now, here's something interesting. The main problem is cancer that we're concerned with. The villages in Iran, India, and China that have this radiation, they're in an area where some villages have high radiation, other ones don't. Nobody can find a difference in the cancer risk of residents of the high radiation villages versus the low radiation villages. In other words, if you're down that low, there's not much damage going on, which is, of course, what we want. So the next question is the radiation in equatorial low Earth orbit below 20 millisieverts per year? Okay, NASA has given a great gift to the world called Alteris. Look at the bottom here. Alteris is a web front end to some very sophisticated radiation codes. And if you tell Alteris a start date and an end date, and an orbit to be in, and the amount of shielding to use, it will tell you how many millisieverts of radiation you will receive. Okay? So let's look at deep space first. And these calculations I did. I didn't get them from some other source. So here is the data for polyethylene, if you're using that for shielding. Here for water, if you're using that for shielding. And here for lunar regolith, if you're using that for shielding. This first row is with no shielding at all. You get 462 millisieverts per year. Okay. Now, the red means that it's too high, and the white means that it's okay. So you can readily see that with polyethylene and water, you need about 7 tons of material to give you adequate protection to get you below 20 millisieverts per year. But if you use lunar regolith, you need 11 tons per square meter. Okay. Now, what about equatorial low Earth orbit? Here we go, Leo. So here we go, tons of material. Notice these numbers are much smaller. Here's for 500 kilometers up, and this is polyethylene shielding. 600 kilometers is also 600 kilometers is also a polyethylene, but it's a little different. Now here's the kicker. Notice that this guy is white with no radiation shielding at all in a 500 kilometer circular orbit with zero inclination right over the equator. You do not need any radiation material at all. Okay? Now you might want to have some, but you don't need it. Okay. Now, if you go to 600 kilometers, you got to be a little, it's going to cost you 50 kilograms per square meter. Okay. But you know something? Remember I said a start date and end date? The radiation levels for any time period are different from any other time period. They're never the same. So you always have to tell Oteros when you want to do the calculations on. And in this case, we deliberately chose bad years that had a lot of radiation, and we simulate for 1 year. But for settlers, you're really concerned about the average over many decades. So I did some calculations using 1965 all the way to 2017, as if you're in orbit that whole time. And then I said, okay, the hull gives you some radiation shielding, and the life support system has got a lot of water in it, and that provides you with radiation shielding. So there is some radiation shielding you're going to get for free, you don't need. So I modeled that with it's a half ton of material with this composition. And when I did those calculations, basically what it said is if you go up to about 650 kilometers, that you're okay. But if you go any higher, you aren't. Okay. So by now, I think I should have convinced you that you don't need radiation shielding, maybe not very much radiation shielding, if you go in the right orbit. So now I'm going to go to the second part. So we've made our settlement much lighter weight, and we put it much closer to the Earth in our minds. Okay. Now we're going to make it smaller. Now, as we've noted before, the Stanford torus rotates at 1 RPM, and that means to get 1 G of force, so it feels like you're on Earth, 1,790 meters. However, if we could run it at 4 RPM, it would only be 112 meters. Okay. The problem is if you rotate people, they get sick. There are a bunch of experiments done with rotating rooms. These are rooms that just rotate between 0 and 10 RPM to see what happened to people in a rotating environment. In this one particular experiment, and there's lots of experiments that have similar results, at about 1.7 RPM, people started to get queasy. At 2.2 RPM, one subject threw up, but otherwise it's pretty much the same. When they got close to 4 RPM, symptoms got to be mild, not very mild, but here's the kicker. Subjects adapted within a day. Yes, if you go to Colpina 2, you will get sick, but you won't get sick for very long. And this is not going to deter somebody who wants to settle there. It might mean that you don't want to go visit for a weekend because you'll be sick the whole weekend, possibly. But if you're going to go there for 20 years, it doesn't really matter. Now you can rotate faster. They did experiments, almost up to 6 RPM in this particular case. But look at 6 RPM, you've got a diameter of 50 meters. That's an awful small place to live in. I don't think I want to do that. And even then, most adapted within a day anyways. So good. So what happens if you take the Stanford torus or Colpina 1 and you run the 2 keys, the first 2 keys on it? There's big consequences. Consider the Stanford torus. It's a 1 RPM system, 1,790 meters in diameter. I know I'm being repetitious. There's a reason for that. It weighs 13 million tons. It has almost 20,000 residents. If you now shrink it down to 112 meters diameter, this is in your mind, rotate it at 4 RPM, put it in equatorial LEO, protected by the Earth's magnetic field, get rid of the radiation shielding, okay, then it weighs 2,000 tons with 120 residents. That's too small. Besides, I like cylinders. So let's look at Colpina 1. It's 2 RPM, 450 meters in diameter, 4 million tons of material, almost 8,000 residents. So we're going to shrink it down to 112 meters diameter. We're going to spin it at 4 RPM in our minds. We're going to put it in LEO, E-LEO, protected by the Earth's magnetic field, get rid of the radiation shielding, and we get a settlement that weighs 8,500 tons with 500 residents, and I want to live there. Okay. We have to get the material from Earth, where it is now, up into low Earth orbit. And the key to that is reusable. Until recently, most vehicles were thrown away after one use. It's as if you bought a car, drove it one time and threw it away. You wouldn't drive much cars, you know? Okay. Reusable, high flight rate, because reusable doesn't work without high flight rate. We'll get into that. Launchers. Now, if we were trying to do this 10 years ago, we would have to use the shuttle. The shuttle is a wonderful machine, but it costs $20,000 to get a kilogram of stuff into low Earth orbit. Now you multiply that by 8.5 kilotons of material, and you got a number that is way too big to pay for it. Today, things are quite a bit better. This is the Falcon Heavy. You can tell because it's got the 3 cores, okay? It costs about $1,400 per kilogram to put material in low Earth orbit. And it has flown a few times. So that's promising. So what if we figure out how much it would cost a person to pay for their share of the materials and a seat to get there? So let's look at this column right here. The Falcon 9, which is the same thing as this, but without the 2 boosters on the side. The Falcon 9 can be used to take people up there. And the Falcon Heavy can be used to take the material. Now the Heavy is going to lift 17 tons of material, because that's the one settler's share of the mass of Kalpana 2. Unfortunately, a seat to get up there is $18 million. So you put those together and you get $42 million to move into Kalpana 2. I don't have that kind of money. I doubt that anybody in this room has that kind of money or ever will. It's too much, not going to work. But there is a vehicle under development that if they meet their goals, and SpaceX has been known to meet their goals, albeit late, but they meet their goals, could do the job. And it's called the Starship. This is Photoshop. These are not. This is Photoshop in, okay? This vehicle is very large and it's completely reusable. The Falcon Heavy and the shuttle are only partly reusable. It is plausible, not guaranteed, plausible that by the time it becomes operational, because it's in flight test now, it will be able to take stuff up into space for $70 a kilogram. Now, what if we put that in our little column? Okay. Now, I use $100,000 for flying to low Earth orbit because Elon Musk has said, Elon Musk is the CEO of SpaceX, but they expect to fly the Starship to Mars for $200,000 a seat. Well, if you can get to Mars for $200,000, you can get to low Earth orbit for $100,000. Okay. And if you put that all together, you get $1.3 million. A lot of people have that kind of money. In the United States, a very successful engineer or dentist or doctor can save that, and if they invest and save, can have that kind of money laying around. Okay? It's all they've got, but it can be done. Okay. However, there's a problem. You're not going to get to this number if you just have 1 or 2 vehicles and you fly them every couple of weeks. You know, if you've got a vehicle to fly every day and you'll only fly it once a month, it's 30 times, almost 30 times more expensive than if you flew every day. And today there are less than 100 flights per year. So if you had a vehicle that could fly once a week, 2 of them would be sufficient. 2. Okay? It doesn't work. I think you need, and this is really a guesstimate, at least 10,000 flights per year to get economies of scale, to allow for this $70 per kilogram. So what markets might do that? I'm going to start with the most speculative organs. They are actually printing organs in space right now. Okay? They're doing this on an experimental basis. They can't destroy your heart. But the reason that you want to do that in space, you want to do it in microgravity, okay, is if you do this on Earth and you build up your heart, at some point it will collapse because it doesn't have any fluid to support it. Okay. So we can solve that problem. So here's the idea. You take a cheek swab, as you may have done for the pandemic, and you get some DNA, you send it up to the production facility. It takes that DNA, puts it in a cell, or maybe just uses those cells and tricks them, but it basically tricks that cell into growing a heart, okay? Then you ship it down and you stick it in you and you have a heart. Nobody died. If you want to get a heart today, somebody's got to die. Nobody has to die, okay? And second, it's your DNA, so it should not be rejected. That's one thing. Earth point to point. You can get from anywhere on Earth to anywhere else on Earth in about an hour and a half, an hour to an hour and a half, in a vehicle like the Starship, okay? Any suborbital vehicle, actually. So here's the scenario. You're a high-powered New York executive. You have to close a deal with your counterpart in Mumbai. So you hop on the shuttle in the morning, you get there in time for a working lunch, sign all the paperwork, hop on the shuttle, get back to New York in time for your daughter's soccer game. That's what you can do. A little pricey, but you can do it. Okay. Next one is solar space solar power. Basic idea is you gather energy in space and you beam it to Earth. This can be an enormous supply of very reliable, very clean, no carbon emissions in operations. And the reason it hasn't worked is it's too expensive. But most of the cost, or a lot of the cost, was due to launch costs. And launch costs went down a whole lot. So it's time to revisit space solar power and see if we can't get those huge amounts of clean energy, which of course will give you a high flight rate. And tourism, lots of tourists like to fly. You're getting a high flight rate that. In addition, tourism gives you incremental development. So here we are in the International Space Station, which has been used as a hotel. It's not a hotel, but it's been used as one. That we have today. It's government owned and operated. In order to have tourist hotels, we don't want to have them government owned and operated. That would be really silly. And the government can't directly subsidize, rich people flying into space, but the government can and is helping private companies develop space stations. And the thing about a hotel is a much easier version of a station. You don't need all that scientific equipment, right? It makes it easier. So here's the idea. You start small, build a small, a small hotel, then build larger and larger ones until it's the size of Company 2. Then build a couple more to get good at it, and then build Company 2. A short, little incremental step each time on the way. So is tourism up for the job? Well, here's tourism of the past. This is when the ISS was a hotel briefly. There was a total of 8 flights for 7 people. One guy flew twice. They fly on the Russian Soyuz. I have a beautiful image of this, and I could not get it into this presentation. Don't know why. The Russian Soyuz stayed for a week or two, and they averaged $25 million a seat. This number is soft. We don't really know if it's right. It's the best guesstimate that I can find. In addition to paying $25 million to go, you must spend many months studying and training in Russian. Okay, you have to learn Russian to take this flight. And you have to be in Russia for the training. I've been to Russia a couple of times. Wonderful people, miserable weather, I can tell you. This is, and $25 million, you have to learn Russian and spend months and months. It's a lot. The people who did this are tough, smart, capable people, doing amazing things. And the Soyuz is a very cramped vehicle with few amenities. And when I say few amenities, I mean no amenities whatsoever. The landing, for example, has been unfavorably compared to a car crash. So that's the past. Here is the future. This vehicle here is the Dragon Crew vehicle developed by SpaceX. It has flown 2 American citizens from American soil to the International Space Station and brought them back safely. Okay. It's capable of carrying 4 people. It was developed under contract with NASA and fixed price contract with the company providing some of the funds. Boeing has done is building a similar capsule on the same contract, but they're having some difficulty. They had an uncrewed flight test earlier, and they found a lot of problems that have to be dealt with. But I'm certain you will. So where could you go? Well, one thing, you can simply go to orbit and stay there for a few days or whatever. You can go to the ISS. When these guys went up there, that's where they went, the ISS. And the ISS not only have to pay for the flight, but you'll have to pay $35,000 a night for a place to sleep. NASA actually has prices for different products that you can purchase during your stay in the International Space Station. There's also a talk, I don't know how much work has been done, but there's been talk of a lunar flyby. We'd actually launch from Earth, go whip around the moon, and come back and hope your heat shield works well because you're going to come in hot. Come back to Earth. That would be an amazing trip, wouldn't it now? Okay. So how big is the tourist market? Now, obviously, $25 million a seat and learning Russian and training in Russia is steep. We got to get cheaper than that. $18 million for just the Dragon crew to take you up. Okay, obviously you're not going to get a big market. So there have been some studies in the market. Crouch did a study researching the space tourism market, and this is what he found: if your ticket costs $800,000, you would expect about 170 passengers per year. Now, if we could get price down to that $100,000 per flight, that may be possible with the Starship, that would put it right down in here, somewhere between 400,000 passengers and 5 million a year. That's exactly what we need. That's what we need. Something pushing, hundreds of thousands, millions of people want to go into space, and that will get us the flight rate that we need. So, a preliminary financial sketch. Right now, Space Settlement is living off of angels. Jeff Bezos, the owner of Amazon, the CEO of Amazon, puts $1 billion of his Amazon stock into Blue Origin every year. That's a lot of money. Elon Musk has been developing the Falcon 9, the Falcon Heavy, and now the Starship for years now, has put his heart and soul into it and almost lost everything. But we can't depend on angels forever, or even for very long, to tell the truth. We need a more standard model of economic development. And I propose a real estate model where you take out a mortgage and you give a down payment, and then that's how it goes. So the idea is the purchase price includes a private condo for your living and a share of the hull, the power, the thermal, all that sort of stuff. So you own the land. Okay. For a couple, we think this would cost about $1 million down and $4 million for a $4 million mortgage. Now, that's a very optimistic number. I don't think it's absurd, but it's bordering on it. It's very optimistic. But maybe one more generation does start it. We'll see. So the $1 million down, you presumably saved up in your good job as a doctor or a dentist or whatever, and the 4.2 million is you have to borrow. So the problem of financing the first space settlement boils down to paying the mortgage, $4 million mortgage. So how do you do that? Well, the first thing is don't quit your day job. Okay. The job that earned you $1 million to buy, the down payment, that same job very well may be able to be done remotely. We found out a lot about that with the pandemic. A lot of jobs can be done remotely. So keep your job. Keep the same job and use it to pay down that $4.2 million mortgage. Because component 2 is very close to Earth. You can be completely integrated into the internet. Completely integrated, become totally seamless. Okay? So that's the first step. The second step is to do something where you have a competitive advantage. And that would be taking satellites that are too big to fit in a single rocket launch and launching the pieces up to component 2 and then putting it together properly, test, and check out, make sure everything is working fine, and then send it on its way to wherever it's supposed to go. This is particularly important for space solar power, because space solar power involves satellites that are kilometers in size in order to generate sufficient power for Earth. I mean, many kilometers, 10 times, 20 kilometers in size, okay? Now, if I was going to build a space solar power system, I would not build Colony 2 first. It's a diversion. Build the thing you're trying to build. But if Colony 2 was already there, inhabited by 500 very space-savvy people who understood space way better than anybody on Earth, I'd hire them. Absolutely, I'd hire them. And that's, that's a big business. The government also has to play a role. This isn't going to happen without the help of government. Sorry, libertarians. The government is pretty good at things like technology development, facilities. SpaceX, for example, used the ArcJet facility at NASA Ames Research Center to test their heat shields. Software development, expertise, standards development, testing, all these sorts of things government is good at, particularly NASA. It's also perfectly reasonable to provide development funds. I would not recommend to provide all of those funds, make companies have skin in the game, but give them a little help, make it go. And the government can be a good customer. So here's the inside of your home, which you've seen before, the view out your window. And remember I said at the beginning that maybe by the end, this would make more sense to you? I'm going to go over it one more time and see if it doesn't make sense this time. If you're trying to build a small, easy to build settlement to get started, a starter settlement, if you will, there are 4 keys. The first is put it close, put it in equatorial low Earth orbit, because that keeps the radiation down too. Make it small, rotate at 4 RPM, that means it's only 112 meters in diameter. Make it take the reusable high flight rate launches that are coming in order to launch it from Earth. And it turns out that's reasonable. And then build up incrementally for bigger and bigger hotels until you get to the size of Colony 2, and you just built your first space settlement. And here is a shameless plug for my book, and I thank you for your kind attention.